You just heard from Oscar in the last session. I guess I don't really need to repeat your bio, but I will say that Oscar has a PhD from Texas A&M, and he's focusing on developing tools for drones that could help advance remote sensing science related to oil thickness, in situ burning, and air quality monitoring. And I guess that's what you're going to talk about right now, characterization of smoke plumes from oil spill ISB using UAS.
Okay, yes. Again, thank you so much, Judd. You guys are amazing. How much work and how useful is this workshop? It's always like that. In this case, I think I have also new to show. New in the sense that it's pretty new actually. So data that we were able to collect about a month ago. So I'm very excited to share with you this. I'm going to be talking about how we can use UAS on in situ burning experiments. So just to give you some recap about the ISBs, some of these ISBs are different in nature, not only because of the amount of oil that is used, but also because of the location where they are, and more importantly, because of the weather conditions on which they occur. This is actually the main factor. Contrary to oil spills, oil spills we worry about when we are measuring or mapping the oil spills themselves. So we're worried about thickness, etc. So in this case, I guess the main factor we look after the ISBs is the weather. How's the wind blowing? How's the wind? The atmospheric pressure, rain is going to affect the development of the ISB. So in this regard, the UAS play a major role on the monitoring and identification of the ISBs. The first thing is it will be safety. So we don't have to be next to the ISBs. We can be at a certain distance from the ISBs. The monitoring on real time, it provides a unique awareness of where is the smoke, how close are the features that I need to be aware, how's the smoke developing. So that monitoring on real time is very special. But for my case, for what I am interested on these ISBs is the data that we can collect when this is happening. And the data I'm talking about imaging, the imaging for performing maps that will tell you before the smoke, what were the surrounding conditions on the spill, and after the smoke, how far the smoke reached the areas where the smoke left where the fire left a fingerprint. But also, if we can measure somehow the emissions coming from the smoke is also very important, because it's a developing science where we are still learning and trying to understand the concentrations of these pollutants from heavy, dense smoke, how far they are going to be reaching. So if we can somehow measure and monitor these emissions, is going to be very important. Another piece of information that we are developing is 3D imaging of the smoke. Why is that important? Because, well, if somehow we could, with drone operations, reproduce a 3D volumetric representation of the smoke, it can be used for many things. For example, determining the volume of the pollutant and the rate of burning, for example, can be used for that, for many different applications. So that's another area where we can use UAS for that. Of course, the quantification of the oil that is being burned, and for NRDA purposes. So I see drones to be, again, a very useful tool for monitoring ISBs. So I'm going to show you some examples of ISBs, and I need to say thanks to my colleagues from LOSCO, who has been a very invaluable partner on this type of research. It turns out that Louisiana has had lately on this last years multiple occasions where there has been situations where the ISB will be the most adequate way to deal with a spill. So these examples are going to show some of the different weather conditions. For example, in this case, we see the smoke rising very high, suggests that there was a very low pressure and very low wind. So what that means is that the smoke, instead of moving horizontally, is just rising vertically almost, and that's how the conditions were in this case. This other case, for example, the burn, it was as well very low pressure. The smoke rise, and then it gets to a certain point, reaches a boundary condition, and then the smoke starts traveling horizontally. And the cases are, you know, depending on the weather situations, are going to be different from case to case. I'm going to show you actually a situation that we had a month ago here in Louisiana. It was reported on January the 21st. There was a small spill. Coast Guard, LOSCO, NOAA was present evaluating the situation, and part of the job was to monitor the evolution of this spill, of this burn. So what I'm going to show you here is the area, the general area. So the panel on your right shows it was next to the Mississippi River. What I'm going to show you here is a map that we produced, again, using multispectral data. The reason we use multispectral data was because the RGB is actually not the best to identify where the oil is. So we wanted to be able to generate a footprint of where the oil was before the burn. And again, same map of the area, almost at the end of the burn, as you are seeing it here. So, as I said, we use the multispectral data before the burn to see what is that area where the oil has a fingerprint on the surface. It happens that because we have such a variability on the land and the vegetation inside that booming area, it's not going to be all fully covered by oil. Some areas going to have vegetation and probably higher land where the oil wasn't there. Anyway, so I'm going to show you now. I'm going to stop here. I'm going to switch gears to this. Yes. So this video, I hope it plays well. It's just going to show. It's going to show the case that we had. This is the burn that was happening. It was on January the 21st, and this is, before I talk about the burn, I'm going to show you a sensor that we developed here in WaterMapping over the last months. So this sensor it has a chamber. It has two chambers where we use these fans to funnel the smoke through these sensors. And basically, we can detect all of these elements or different compounds of gases. For example, we can see isobutane, propane, toluene, ammonium, carbon dioxide, monoxide, and also methane, ammonia, benzene, etc. So I think one of the most important was actually not listed here is the ppms, the particles per million of the dust or the smoke are very important because it will show the density, how dense the smoke is. So we can measure 1, 2.5, and 10 microns of smoke particles. This sensor can be mounted on a drone, and it measures also temperature, humidity, atmospheric pressure, and GPS every second. So the point is to basically fly over the smoke and then collect all these measurements on real time. On real time is important because it will let you see if you are inside the smoke plume or not. Anyway, so let me see. I'm going to let this play a little bit. And then, so this is a new system. Now, actually, we're making a different version that is only going to have 4 sensors, much smaller. This one in here, as you can see, it's about the size of a shoebox, 10 by 8 by 5 inches. It weighs about 4 pounds, and it can last for 4 hours. It's still a little bit bulky for a small drone, for a medium-sized drone. I don't think you can fly this with only with a very large drone, but we are making a new version where we can reduce the size and the weight. Is the newest one is going to be about 1.5 pounds. Still can be flown from a mid-sized drone. Okay, I'm actually going to show an example of how this is mounted on the drone. We're using a very large drone. I probably is one of the largest ones available commercially. This drone is the Alta X. It's just to give you a sense of the scale, from tip to tip of these props, it's about 7.5 feet. So it's a big drone, but it can carry, well, so here actually we have it with about 20 pounds or 20 plus pounds of payload. And in this test, we are using this is a previous version of the sensor that I just showed you, and it has also a mock of the Colibri, which is the sensor that the EPA uses. I think Brian Goulet is the main investigator for that, so you will have to refer to question about the Colibri to him. But this system was configured and made particularly for a test that we want to do at Creel in the coming months, if COVID allows to do that someday. But this system also has multispectral cameras and thermal cameras. So the advantage of this heavy-duty drone is that obviously we can put, it's like a Christmas tree. We can put as many sensors and cameras we can possibly have. Is carrying about 25 pounds of payload. It's really an advantage. So this video is gonna go back to the previous case on the smoke plume that I was showing you, which you'll see the weather is a big factor. As you can see here, it was kind of bad, rainy, cold, very uncomfortable working conditions. Actually, there is a mistake here. It's a typo. It should say wind gust, not wind gusts. But you get a picture of how difficult it was to operate there. Next to me, I have Andy from LOSCO and a lady from the Coast Guard. And you can see the distance where we were operating and how far the smoke was. It was a good distance, something like probably about 500 feet, or probably more than that. So again, the drone that I was using at that time provides the real-time thermal and the visual. The thermal is fantastic, particularly working with fires. It really gives a very distinct signature of the fire. I think it has a lot of potential, the thermal, for working or studying heat transfer from the fires and how far this smoke can travel. It's not the topic of this discussion, but I see that the thermal data is going to be also a matter for development for remote sensing on fires for sure. But anyway, so this is just to give you a perspective of how the fire was evolving, and this is going to be now a perspective from the ground. And so in this case, we had an atmospheric inversion. What is that? Well, we have the wind, the temperature, the rain didn't let this smoke to rise. It was mostly horizontal displacement more than vertical displacement. So this video is going to show you how we can, with this imaging capability, we can measure and track specific areas of the smoke, so we can see how fast the smoke is moving. Why is that important? Well, we want to develop models that can, we can backtrack and produce a good enough model that we can, replicate all this smoke and understand all the conditions around the smoke. So there is many things to watch on this video. But again, so I'm going to stop this for a second. I want to say, so things that we look on the smoke. Okay, where is the source? How far is traveling? How fast is traveling? And the dispersion on the smoke produce this delta that we want to measure and see at a given distance how much vertically and horizontally the smoke is being displaced. So we look at all of those things and we try to measure that. So we basically ingest all of these conditions into a numerical model, and and then we see how well we can reproduce what we observe on the field. So it's going to come up in a second here. Model initialization. Oh yeah, so well, I mean, you'll see we use the videos, we go back and forth, fast forward, and reverse, so we can track a specific clusters of this smoke. Well, I missed to say it, but so the vertical elevation of the smoke varies. I missed my point there, but anyway, so going with this video, so you'll see here the model that we reproduce is a Gaussian model. It's the most simplistic model, 3D model that you can see, but it's pretty good because I think for the conditions, the Gaussian model work well in terms of we don't have terrain elevations that are gonna affect how the wind is gonna displace or affect the displacement of these particles. Anyway, so the model basically generates all these particles, and the particles are gonna have basically attributes about the concentration. Oh, I explain this wrong. The amount of concentration per particle for each of the elements. Anyway, so let me go back here. So again, unfortunately, on that case, because of the weather conditions, I couldn't use this gas sensor, but still, I think the collection of data was really good. Allow us to see displacement and modeling. On an ideal world, if we build this type of sensors where we'll be, waterproof, then, we can use them, but we are not there yet. So this is just different views of the sensor with all the types of elements that we can measure. Play the video. Okay, yeah. So we made a website that we figured out a way to report on real time the data from this drone. It's kind of funny, but the way we did it, basically, we have to put a cell phone, a smart cell phone inside the drone. And
I think we've lost you, Oscar.
Well, anyway, so I think that's a small detail, but I think I can just close by saying that basically all of these observations from the drone, I don't know if you saw the video, but basically we're using all of this information. The imaging is the most important aspect. Actually, we were talking with some friends from NOAA to expect some feedback. Some people is more interested on the particle information from the gas sensor. I think the imaging, the visualization is also a big factor for generating these models. I'm sorry, I lost my fluency here, but I want to say, so we have a tool. We have a tool that we can use from UAS to characterize ISBs, and I think there is two main components. One is the measuring of concentrations, and then the imaging conditions are crucial. I don't know if anybody has a question. Should I stop here, Joad, and let David?
Yeah, we do have a couple questions.
Yeah. Yes.
So from Shauna Clark, thank you, Oscar. When incidents like the January 21st event with the RRT-6 occur, does WM own the data and reserve it? Or is it uploaded to a US EPA or other data sharing system in order for other researchers to learn from and evaluate? Thanks for sharing, and gig 'em.
Oh, well, that's a great question. We operate in a cooperative manner. So if anybody is interested with the data, so we can, all work together, I'm more than happy to share it. We haven't actually created a mechanism to share it, but please contact me, and I'll be more than happy to make it available.
And we have one more question. Why would you have high NH4 in the plume? Oil is not a nitrogen-rich substance. Any validation for that?
Excuse me, could you repeat the question?
Why would you have high NH4 in the plume? Oil is not a nitrogen-rich substance. Any validation?
Yes, well, this sensor wasn't thought to be specifically for ISBs, but also open to other emissions. So it was meant to follow the learning experiences from other sensors like the EPA and others that we have seen. So we thought that since as I say, this is a Christmas tree, we can hang whatever we want. So we thought, what else we can measure? Okay, ammonia and NOx and things like that. So that's the reason why we added.
All right, thanks. That's all the questions that I saw.
Okay.
Thank you, John.
And thank you, Oscar. Thank you for bearing with us, and it was informative, okay?
Thank you.